Okay, so, and I did all the odds, right? Is that kind of what I did? Am I remembering yesterday? Okay. Okay, so what kind of questions did you have on the evens? All right. So number 8 on the back. It says the length of films in Hollywood are known to be distributed with a mean of 115 and a standard deviation of 15. Okay, find the probability that a single randomly chosen film is less than 95 minutes in length. Okay, so you're going to do normal CDF. Is that showing up there? Normal CDF. So you want to have something small. So put 0 here to 95, and then you're going to do 115 and the 15. Okay? And the reason why you're not changing your standard deviation is one that is said we're only going to choose one film. So if you still use the equation, you're putting the square root of 1 in. Square root of 1 is just 1. So that's why it changes. So this comes out to roughly a 9.12% chance that if you randomly selected some film from Hollywood, that it would be less than 95 minutes in length. So what this is basically finding is you're finding that area is what you're looking for on the this is supposed to be a normal curve. It's not supposed to be jagged. Okay. What else did you see I could help you with? Feel okay? All right, so we did that. Yeah. Are we still feeling comfortable with this chapter so far? Okay, so let's see. We're going to step into 5.5. Let's see what we do on these notes. Where are we at? 5-5. There it is. Okay, so 5-5 notes. So I'm on page 10 of your book. So this is section 5-5. Okay, so this is where we're going to start getting kind of a plethora of information. So I'm just warning you, I'm going to go slow. Please stop me, and we will struggle through it together if that's okay. So proportions are percent and decimal form. Also form normal distribution sampling distributions for large random samples. Before you get into calculation, we'll define some terms. So if you see a P and there's nothing with it, this is the population proportion. So remember, the proportion is the ratio or fraction or decimal, not as a percent. Okay? If you gave it to you as a percent, then you have to move the decimal over and put it back into standard form. But then we're going to call something this. We're going to call this P, and they refer to this as hat. Okay? Because it looks like it's wearing a little hat, I guess. This is the sample proportion. So there's a difference between the sample and the population. Population is everything. Sample is who do we select from some sort of random number generator. And then you have mu of p hat. So this is the average population or average proportion of all random samples. So what this one means, samples, what this means is you did multiple collections of information. You ran a study, you randomly selected a group, you get your information. You decide, okay, I want more. So you do another study, doing all the parameters are the same, how you did data collection are the same to go with that more and more and more. And then you have this, And this is the standard deviation. Of all proportions of all random samples. So we're introducing a couple of different letters that we need to take a look at. Okay. So everything's good so far? All right, so they give an example. They say, assume that 25% of all people have type O blood. So let's stop there. So all population have type O blood. Okay, so that just refers worldwide. Okay, so then we conduct a random sample. So 25% of people assume that all. So this would be then just P. Okay. Okay, I guess we should convert this to 0.25 if we're going to call it P. Okay, seem good? All right, so then we say we conduct a random sample of 100 people and obtain their blood pressure. So we have a random sample. We have the sample of 100 people. Now, is this a good amount of people to do a study of? What was the number? Was kind of our 30. Yeah, so above 30 is we start noticing. Okay, there are things you can do if you have less than 30, and there's a term that is later probably going to be introduced called degrees of freedom, but it's going to take place. So let's take a look at the p hat of what this would be. So we conduct a sample of 100 people, and 28 of the 100 have type O. So now our p without any fancy characters is 0.25. Our p hat is 0.28. Agree with the math so far? So this is from our sample. So does that mean that the overall population is wrong when we're saying 25%? Or could we have done the study again and perhaps we get a different 28 out of 100? We get a different number. Could this number change for us if we do another study doing the same way, collecting data? Okay, so this just happened because that was what that population showed. Okay, if we do more and more studies, we're going to get closer and closer to the 0.25. So it's not, if you do one sample and you find you at 0.28, it doesn't mean that you can say, well, the whole population's wrong. Okay, because there is some sort of standard deviation that takes place with it. Okay, we expect the proportion of people with type O blood to vary somewhat. So this is variant. 28 versus 25, or 28% versus 25%. There's some variance in there. Okay, it's known to happen, and it's not because you did something wrong. These varied random samples for sample and distribution with mean, so UP, and standard error. All right, that's UP hat. And standard error. Okay, so the formulas for these are UP hat, or it's mu actually, is P. Okay, and then our standard deviation that's going to change is this. We're going to go P minus 1 minus P over N. Okay? So, this is just the number of studies. So let's talk about that, or number of people that we sampled. So if we take our above population and we want to find out this new version, we're going to say, we know that this is UP hat. Is that an error? Hang on, I'm looking at this. UP hat. All possible. Okay, all possible. So that's this is 0.25 because UP is the average proportion of all possible random samples. So this is going to be what P is as well. Okay, so we've said that. We've defined that. It's from above. So then we're going to use our equation. So we're going to go 0.25, and we're going to go 1 minus 0.25, and that's all going to be over 100, and then you could easily plug that into a calculator. So you're going to come up with 0.0433, which means we're talking about 4.3%. Okay, so that's like a different standard deviation that's going to take place. That's how you have to look at that. Okay, the interpretation of each statistic is simple, that for a random sample of size 100, we expect to see 25% with type O blood, but we typically vary from that mean or from that average by 4.3%. So here's the question. This is 25%. This is 28%. So when we vary, meaning we're going to be within one standard deviation of it, is from 25 to 28, that's only 3%. So that falls within that parameter. Okay, it means, okay, yeah, there are things that happen. I got lucky that I selected, of the 100 people I selected, 28 fell into this. So if I do the study again, I might get 23 out of 100 with a type O blood, and that still falls within it. It doesn't mean things are going wrong. It just means that you realize your wiggle room, your fudge factor or something like that is within 4.3%. That's where you're feeling your data should happen. Can the distribution of a proportion also from the can the distribution of a proportion also form a sampling distribution? Yes. However, the central limit theorem tells us the sample size must be large enough. So what should our sample size be? At least 30 or more. Okay, good. So in principle, the three assumptions that must be met to ensure normal sampling distribution for proportions are the same as for the means. So you have a random assignment, and I can't emphasize enough for a random assignment. I already said that you as a person can't go walk up to a group of people and randomly select people. There are too many variables that are making you select people. Okay, especially if it's like, oh, that looks like my Uncle Billy. I'm going to pick that person. Okay, there's different things that are going to take. So you have to basically give numbers, look at a random number generator, figure out who you're going to select. Okay, so the individual selections in the sample, we were randomly chosen from a population of interest. And this implies that each individual in the population of interest had an equal chance to participate. So again, the randomization could be like the slips of paper, unless you're this guy who does what with slips of paper and things. I crumble it up. I make it wrinkly. So when you reach in, you're like, I have a better chance that mine, oh, here, that happened. Okay, independence. The probability that an individual's response was unaffected by the conditions by which other selections were made. Okay, so let's say you're randomly selecting and you came across somebody who was in a wheelchair. You can't say, we're going to discount that person. No, that person in the wheelchair, somebody who is different in some form, can't be discounted. You have to say, yeah, that happened to be part of my sample. Sample size is large enough. Small sample sizes suffer from high variability. You don't want to draw conclusions about the population based on a small sample. So again, you want 30 or more. Okay, you could still do it if you had less than 30. And as I said later, you're going to come across something called degrees of freedom that we'll talk about it. Okay, so for the means of the random sample, simply to be 30 or larger gives us the confidence that the sampling distribution will be normal. For proportions, the rule of thumb is a bit different. The sample size is large enough, assumption is met if both of the following are true. Okay, so they're saying NP is greater than or equal to 10. And then N is 1 minus P is greater than or equal to 10. So the N is your sample size. The P is the population proportion, and then 10 is just 10. So n and p being these are being multiplied. There's your algebra. Okay, n again is your sample size. 1 is just 1. P is the population proportion. Now, these two things look very similar, but one of them we're going 1 minus the same thing. So they're very similar types of equations. So in general, sampling distributions or proportions are more skewed as p approaches 0 or 1. The rule of thumb above requires large sample sizes with values of p that are farther from 0.50 to overcome skewness. The normal distribution for type O blood example can be created because all three assumptions are made. Show the sampling distribution below. So what we could do is we could do this. We could say we know that we have an average, we have a mean of 25%. But then we realize that 4.3% is basically what's going to take place. So this is going to go to 29.3 for 1 standard deviation that way. Let's see, 4.3 second, going to be 20.7%. And those are written as percentage. You could write them as just true decimals as well. Okay, yes, I could go up further. I mean, you could add another 4.3, subtract another 4.3, keep going. So that's how your normal distribution would start taking place. So it's once you've created this, you know this from your population, and you go from that. And you can start seeing, did we get our information? Did it fall somewhere here, or did it fall somewhere here? If it fell within that 1 standard deviation, it's very much acceptable. It is very possible, though, that you might find something that falls way out here. Okay? There is that chance that you randomly select of 100 people that all 100 of those people had type O blood. So that's very obscure that happened. It was a weird anomaly, but the chances can happen that will make that take place. This is where, sorry, I got to bring Vegas back into this. Have any of you been into a casino before? Raise your hand if you've been into a casino. So what are some things that you recognize in the casino just that you observed, other than people being drunk and belligerent?
Pew, pew, pew.
Yeah, there's noises. There's all kinds of things that you're hearing. Okay? Now, back when I was living in Vegas, they used to actually have coins come out of the slot machines. Now they give you a ticket. And the ticket you then take to the cashier's cage, turn that in, and they'll give you the money you earn. But back then, the sound that the coins made as it was hitting the bucket below, they did a lot of things on purpose. Now, I know I have people here who are musically inclined. Okay, music people. What is the most calming note? A, B, C, D. What's the most calming note? Anyone know? It's C. It's C. So every noise you hear in the casino that's coming from the machines is C. It could be an octave above or 2 octaves above, octaves below, but it's a C octave. Because your ears hear that and you're like, oh, that's kind of nice. They're not going to change it. They're not going to have this machine making noises as a C, the note of C, and this machine over here being an F sharp. Okay? That doesn't sound right in your head. You're like, ooh, I don't like that sound. I'm going to move away from it, because you hear them together, you kind of have destructive interference. And it sounds goofy, but those are just some things that are taking place. But other things that you should see in Vegas is they do have, I call them idiot boards. And an idiot board is this. They list all of the things that had happened in previous routines on like craps and roulette. So when you see it, you're like, oh, I'm going to go throw money on this because it's going to happen again. Look how often the number 13 showed up on the roulette wheel. I'm going to bet on 13 because it's showing it. No, it's just a sequence of events. So let's have you just do a quick try / look over of 5-5, so 75-76. You do not have that completed. I will not be checking it off tomorrow. We will definitely go over it and work through it together, okay? Have a great day, friends. Take care of one another.